Hello everyone, Paul Stechik with NEPSI, and welcome to this Tech Talk, this EESA, Electric Energy Society of Australia, Tech Talk on power factor and power factor correction, why we should care about it. Before we get started on the presentation, there are some housekeeping things. Number one is I will be presenting on September 1st. Again, I think I'll be talking about harmonic analysis. If there's another subject matter related to reactive compensation, please come back to me and tell me that, because I think I had presented before to EESA on harmonic analysis. And then also another presentation on December 1st, 10 a.m., both of these at 10 a.m. on Wednesdays, we'll be talking about harmonic filter design. And that's a really good presentation, the harmonic filter design Tech Talk, how to rate the components. My background, for those who do not know, is reactive compensation. I've been doing it for nearly 25 years. Reactive compensation, developing harmonic filter systems and capacitor banks for the industrial and utility marketplaces, primarily in North America. Locally to you guys, there's a person named John Wright Smith from American Superconductor. And for those who do not know, American Superconductor purchased NEPSI, a North American company, back in this past October. AMSC produces reactive compensation solutions in the form of STATCOMs, and these are a static device, power electronic type device that produces reactive compensation. NEPSI produces passive compensation solutions in the form of capacitor banks and harmonic filter banks, and this picture here clearly shows a very large capacitor bank, actually a harmonic filter bank for a mine project in Peru. It's 54 megabars. So today's discussion is about power factor correction, and reactive compensation. If you got questions, go to the chat box and ask questions in the chat box. You need to be logged into YouTube or onto a YouTube channel with your logon or with Gmail or something, but you need to be logged on to YouTube to ask questions. So please do ask questions. It makes it more interactive. I will be glancing over on my screen to the left to check for those questions and to answer those questions as we move along. We will be just about 1 hour today for this presentation. We also give out PDH certificates. At the end of the presentation, send me an email, and please take note of the email address here. It's paul.stechik@nepsi.com. It's in the lower left here. paul.stechik@nepsi.com. We give out PDH credits. It's something that we do in North America. It's professional development hours. I do not know if it applies to you in Australia, but if you need to keep your engineering credits up, your professional development hours, we will send you a certificate. It will be worth the amount of time we spend on it. So about 1 hour today would be worth one PDH certificate. So today's presentation is power factor and why we care about it. And I usually like to start off with this power factor discussion with just what the definition is. And it's a formula. Power factor equals the kW divided by the kVA. So kW, remember, that's kilowatts, and apparent power, kVA in the denominator. And that's equal to cosine theta. Theta is often referred to as the power factor angle. And you can see down here that the power factor angle is the phase angle difference between the voltage and the current. In this case, the voltage is blue and the current is red. And this would be a lagging power factor, what we show here. So that's theta. Also, consequently, theta also is related to the impedance angle. If you have a load, it has an impedance. It's got an X component, a reactive component. That reactive component can be either capacitive or inductive, and it also has a resistive component. So when you think about a motor, it has some reactive component, and it also has a resistive component. Reactance is measured in ohms, and it could either be inductive or capacitive. And then you have resistance also. That's measured in ohms again, and that's also measured in ohms. So a typical industrial load consists of some X and some R, and obviously as you change the value of X and R here, the value of theta changes. So we're going to be talking about power factor today, and the load here, R and JX. And I hope I can explain this very well. It's a very basic concept, but But for those who may not be involved in the electrical industry, this is a great presentation on power factor. So there's some analogies that you commonly see, and you got this beer analogy, and it's nighttime here in North America, so I thought about bringing myself a Guinness. And a Guinness has a poor power factor because when you pour the Guinness, the little nitro bubble on the inside pops and you get a lot of foam. And I've always thought the Guinness beer had a really good look to it when you first pour it. But the power factor is pretty poor. You got this head on the beer, the foam, and that's often, you think about that as power factor or VARs. The VAR is the part of the beer that has really no value to it. And then you get the liquid part that quenches your thirst. That's often considered KW. So you can kind of think of an analogy of the beer where the liquid is KW, kVAR, which is imaginary, as the reactive power. It doesn't produce any real work as the foam in the beer. And then kVA is the summation of those two. I don't particularly care for this analogy, but it's the analogy that most people see. You also got the cappuccino up above there. I like the analogy to the right here. It's a mechanical analogy to power factor, and it's a horse carrying a buggy along a rail. And if you think about the horse can't walk on the rail, okay? It can't walk on that rail, it has to walk off to the side. Part of the force required to pull the trailer along the rail, okay, is perpendicular to the rail, and that's shown here. And part of the force is in the direction of the rail here. So the horse actually has to pull harder, okay, because it's standing off to the edge of the railroad there, the railroad ties or the rail itself. This is a vector analogy, and in power systems, it's a polar quantity. We all learn what to describe power as polar vectors that rotate, right? Phasors. And so this is the vector analogy of that. And you got a real power component, a reactive power component, and obviously, if we know these two values, we can calculate the hypotenuse. And this is really what power factor is, in my opinion. It's the best way to think about it. If you had to push a car, you can sit on the outside of your car and you can open the door and push from the side. You know you can't quite get the same push from over there than if you get behind the car and push directly. And that would be a power factor of 1.0. All the power that I'm putting into the car is being pushed into the car to move it forward, power factor 1. If I'm off to the side and I'm trying to push it, I have some that's pushing it sideways. That's really wasted power, and I would call that reactive power. But remember, reactive power doesn't produce any of the forward motion in this case. It's off to the side, it's pushing in the wrong direction. So it's a great analogy, I think, the horse one instead. This is a great and also a great way of looking at power. Remember that instantaneous power, P, here on the top, the instantaneous power is equal to the instantaneous voltage times the instantaneous current. So over here on the chart, you can see we have a power factor of 1. We have the voltage and current directly in phase, and each ways along this waveform, I'm multiplying the voltage times the current. It's a 1 per unit peak on both the voltage and the current. They're overlying each other. If I multiply this value here, -1 times -1, what I get +1, and that's this gray waveform up here, okay? And then I could take 0 times 0 and have 0 here, and I could take 1 times 1 and have 1 here. So obviously what you get is a waveform, a gray waveform here, and this is the power flow, the instantaneous power flow into a load that has a power factor of 1. Okay, it's a resistive load. It's what I showed down here, resistive load, a value of 1. And if you do the calculation, you get a value of 0.5, the average power flow into the load. So volts times amps along the whole waveform. The average power is into the load. So now I can roll my mouse a little bit here, and you can see that if I were to go to a power factor of 0, and a power factor of 0 represents the voltage and current being 90 degrees out of phase, okay? And in this case, you have the blue and the orange. We multiply those values. This is an inductive an inductive circuit now. The current is lagging the voltage by 90 degrees. And here you can see that that if I multiply the amps times the volts along the whole axis here, I get this gray waveform. And so I'm going to do the math here. -1 times the blue, which is 0, is 0. And then you can kind of see here the math here is some value of 0.5 times 1, about a -0.5. So this is how we're coming up with this math. And we get this gray waveform. So this is the instantaneous power into the load again. And this is an inductor, and it's the instantaneous power into the load. And you can see that the gray waveform now, the average value is the red. We have equal amount of power flow in and an equal amount of power flow out. So a negative and a positive. The average value along the axis here is 0. So no net power is being transferred into the load. So this is how we describe power factor from a sinusoidal standpoint. What's going on here in an inductor is that the current is being used to create the magnetic field, but then the magnetic field collapses on the negative half cycle and sends the power back to the load. So that's we have current flow. If you were to go up to the system and take a measurement here, we do have current flow. We got this orange waveform, right? We have current flow. So you think you have power flow, but the issue is it's going back to the source at each half cycle. So we're just creating a magnetic field and it's collapsing. No real power transfer into the inductor. It's just current flow back and forth. So that's reactive power. That's reactive power. We're creating a magnetic field. And that's the thing about reactive power. It's always creating the magnetic field around the electrical devices that are utilized in industry, being motors, transformers, generators. The power lines themselves have a magnetic field, and the very nature of power and the flow of power through the network requires that we have a magnetic field, and the magnetic field is created by reactive power, and that's what we show. So I can roll the mouse here and show you that for varying amounts of power, you watch the gray curve here and watch the red curve, we get various amounts of power transfer to the load. The most efficient point is a power factor of 1. And then we can go towards the capacitive side and then also the inductive side. So it's a pretty cool way to represent power factor using waveforms, and this is what's going on. But we work with phasors and with RMS values, and we don't work with the sinusoidals as you see here. So we're going to the next slide. And again, ask questions. I see no questions here. If people got questions, please do ask. So oftentimes when we do power factor correction, we actually use a power triangle. It's almost the factor standard. The way we do it is with a power triangle. So if you understand a power triangle, you will very easily understand power factor and power factor analysis, because it really boils down to a very simple triangle. And if you can remember the trigonometry back from high school years, you can easily calculate power factor if you know two of the parameters. So we have values of S, which is the complex power, values of P, which is real power, and the values of Q, which is reactive power. When the system is inductive, we draw Q up. When the system is capacitive, as we show here, we draw Q down. So Q is measured in VARs, remember that. So it could be VARs, kVAR, or megavars. So megavars, kVAR, or VARs. S is measured in kVA, kilovolt amperes. kVA is called complex power or apparent power. We normally denote that as S, and it's on the hypotenuse here. And then P is always drawn horizontally. It's the real power measured in kW or megawatts or watts. So there are the three parameters. And again, remember, if it's an inductive circuit, we draw it up. If it's a capacitive circuit, we draw the arrow down. So you have a negative theta here and a positive theta here. And theta, again, is the power factor angle. Power factor angle measured typically in degrees, but it could be in radians if you're doing your power factor calculations in Excel. Remember, if you're using Excel, Excel uses radians. You got to do the conversion within Excel. So it's a bit tricky there. So remember this component complex power, and that's the value of J. So we're dealing with complex numbers, but complex power is more or less a real component, which is the p-axis or the x-axis in the Cartesian coordinate system, and J is a complex number. You just draw that up. So when we talk about a complex number, you're really just talking about the x and y component, the p and q component. So that's where J is. J is denoting the reactive component, and we use it in power systems to do phasor analysis. It's really what power factor is based upon. If you remember back in the high school years, and we had this in North America. I don't know if this is something that you get in Australia, but it'd be kind of interesting to know. Have you guys heard of SOHCAHTOA? SOHCAHTOA. So here, sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, and tangent equals opposite over adjacent. So basically what it's saying, if you've got the tangent of this angle, it's equal to the opposite, the reactive power, over the adjacent, which is the power P. So Q over P is equal to the tangent of the angle. So you could derive a whole host of equations from SOHCAHTOA. So nobody's hit it in the chat box yet, but have you seen SOHCAHTOA? This is how we have learned to remember basically the power triangle, or how to remember theta, cosine, sine, and tangent. Remember that pure resistance, theta is equal to 0 degrees. In other words, pure resistance, we're drawing the axis here. If it's pure inductance, we're drawing up. If it's purely capacitive, we're drawing down the arrow. And then we're disconnecting the S value, which is the complex power or parent power. Okay, so we often see terminology associated with power factor, one of those being lagging. I have a lagging power factor. What that means is the system is inductive, right? The system is inductive. You say it's lagging. Why do you say it's lagging? It's because the current lags the voltage. Voltage becomes the reference when you're doing power system measurements. You use your voltage as a reference. Is the current lead or lag that voltage waveform? Does the peak come in front or from behind the voltage waveform? Okay, so if the peak comes first, right? If the peak comes first, it means the current is leading the voltage, right? It's leading, or if it's lagging. So we got these terms, leading and lagging. Just associate lagging with inductive, associate capacitive with leading power factor. Okay. In general, industrial plants are going to be inductive. If you don't have no reactive compensation, no power factor correction, then we will say that the system is most likely going to be inductive. Motors, transformers, distribution lines, they all are typically inductive in nature because the magnetic field requirements are greater than the electric field requirements. Okay, so associate the electric field with capacitance, associate the magnetic field with inductance. So power factor 1, again, we're kind of being repetitive here. It means that the PF is 1. We draw a line in our Cartesian coordinate like this. P is equal to S in this case because we have no reactive component. Q is 0, and it's a resistive load. It's purely resistive. In this case, it's a light bulb. It's something that generates heat. And anyways, it's a light bulb, and there is no inductance to that circuit. Okay, so if we think about an inductor, though, purely an inductor, something, a coil, okay, that has a magnetic field around it, purely inductance, we would draw the line up. P would be 0, Q would be equal to S, and we have this symbol over here, which is the symbol of an inductor. You can see here we're using plus J. It's really the y-axis in a Cartesian plane. And in this case, it would be an inductor as you see here. It's creating a magnetic field, and that's how we we show it. Finally, we have a capacitor. A capacitor, you're drawing the vector down, or the phasor down, and it's shown as a minus J. Okay, and in this case, there is no real power being consumed. Capacitors, by the way, a typical capacitor has about 0.05 watts per kVAr. So losses in typical polypropylene power capacitors that you see nowadays is very low, about 0.05 watts per kVAr. So it is basically almost drawn straight down, as you see here, if it was a capacitor bank. So this is an example of power capacitors. They're 2 bushing capacitors, very typical of what is sold around the world. And again, it's something that NEPSI supplies. We supplied the metal enclosed assemblies of those capacitor banks to industrial and utility and renewable power plants, all of the above. We have lots of other tech talks we can do about capacitor banks and how they're put together and things like that if there's interest in that. A typical industrial load is not purely inductive and is not purely capacitive. The reality is industrial loads consist of things like motors, and motors have a power factor maybe 0.85 or 0.9. You have other variable speed drives which may have a power factor of 0.85 again towards 1.0, depending upon if it's the newer active front end drives, you might have a power factor close to 1. You also have rectifiers, right? Rectifiers, power electronic devices that may have power factors in that 0.7 range all the way up through closer to 0.95 power factor. So depending upon what the load is, you're going to have varying amounts of power factor. But most industrial loads, by their nature, are inductive, and they're going to be drawn, as you see here. P to the right on the axis, Q going up, and then you have your complex power. We can have systems where the system is capacitive. We might have a system where it's capacitive, and we would draw it down. But normally, if we go into an industrial plant and the system is capacitive, it means that they already have power factor correction, and the system is leading. So I'm going to go through, look at the chat box real quick. There is somebody that grew up in New York, and that's exactly how they learned it. But that's New York. I was wondering if anybody from Australia learned it with SOHCAHTOA. Victor, what is an example of a capacitive load? Good question. The capacitive load is a capacitor bank, as we've shown here. Capacitor bank, as you see here, is a capacitive load. Other examples are STATCOMs, something that also American Superconductor produces. So STATCOMs is a power electronic device that produces reactive power, but it's being put on a system for the purpose of reactive compensation, because we need to correct power factor. We're going to get into reasons why you want to correct power factor. Other examples are cables. Medium voltage cables are oftentimes capacitive, more capacitive than inductive. So remember, there's a capacitive side of the cable and there's an inductive side of the cable. When current flows in the cable, it produces a magnetic field, and the cable is inductive there. But there's an electric field associated with the cable, and oftentimes cable systems are capacitive in nature. But capacitor banks are primarily the sources for reactive power. And SOHCAHTOA was taught in Australia, or not in Australia. Okay, so you guys had to remember it some other way. How to remember the sine, cosine, and tangent, how to calculate it. So typical lagging power factor, this is the motor. Let's move on. So the three-phase formulas. These are the formulas that we most often use, and I will tell you that three-phase formulas, I almost always work with three-phase power. Very seldom do I work with the single-phase formulas. By and large, medium voltage systems, the systems I'm working with are three phases, and we're working with three-phase loads. But oftentimes, distribution systems consist of single phase lines, right? Single phase laterals that might feed residential customers, and then oftentimes you have to use single phase formulas. So when calculating three-phase power, as you see here, power three-phase is radical 3 times V line to line. Don't forget the radical 3. Don't forget line to line voltage times I, the current in the power line, times cosine theta, which is the power factor angle. Okay, so that's the three-phase power. And that's also equal to the complex power, all right, times the cosine angle. You can come up with the same value there in watts. So a similar value for Q. Always associate power with cosine, associate sine with reactive power, so Q with sine. It's a good way to remember it. Most often, whenever you're talking about reactive power, you're going to be using sine. Whenever you're talking about watts, you're going to be using cosine, those two formulas. So sine is associated with the vertical axis, right? Sine equals the opposite over the hypotenuse, right? Opposite over hypotenuse, where cosine is the adjacent to cosine over the hypotenuse. Okay, and then three-phase, the complex power, the apparent power, is equal to radical 3 times V line to line times the current in the line, is the voltamperes of the line. So I had a power teacher in my third year of college, and he said anybody who would forget the square root of 3 when doing the calculations, he would divide their test score by the square root of 3. And there were some students who, in fact, did forget to use the square root of 3, and he divided the square by square root of 3. So anyways, an interesting way to make sure we remember the square root of 3. But so why should we care about power factor, right? Why should we care about power factor? For North America, it's always associated with potential savings. Not always, but very often is associated with the potential savings. The industrial plants in North America will be charged for poor power factor. And we're going to get into reasons why in a few minutes. But poor power factor on the utility bill, they have a meter outside the industrial facility. It's measuring the kW into the plant and also the reactive power. Residential customers typically do not have a reactive power meter outside of their house, and therefore they're not charged the power factor. They're just charged for their energy consumption. And remember, energy is related to watts, right? Energy is related to watts, real work. And that's what you get charged for the residential bill in North America, never power factor. But for an industrial plant that might have rectifiers, VFD drives, or large motors, reactive power flow in the power lines results in a poor power factor. And if they do not meet a certain power factor, the penalty can be quite large. In fact, paybacks for equipment is oftentimes less than 6 months in North America. That's how much you can be charged for a poor power factor. So another reason why you should care about power factor is voltage regulation. Reactive power flow through an inductive load creates voltage drop. So the worse or the power factor, the more reactive power flow you have, the more voltage drop you have. If you think about an industrial plant, the incoming transformer represents a very large inductance. It's got a leakage impedance associated with it, typically 5 to 10%. And that leakage impedance times the reactive power current, the component of current that's 90 degrees out of phase, the reactive power component, will result in a direct voltage drop on the system. So industrial plants oftentimes are experiencing voltage regulation issues, meaning voltage drop as the load comes up in power due to poor power factor. So if you can correct the power factor at the load and keep the power factor close to 1 as the load comes up, step on capacitors, keep the power factor close to 1, I will control the reactive power flow through the network and therefore reduce the voltage drop across that transformer. Or if it's a large or long distribution line where the line is long, I would reduce the voltage drop across that line. So improving voltage regulation is a key reason, another key reason why you might want to consider improving your power factor. And then finally, system capacity. If you're pushing current through the power system and it's not producing real work, then you have an inefficiency in your system. I'm putting a power line in. The power line has a ampacity rating to it. The transformer has a kVA rating to it. If some of the power that's being pushed through the line is reactive power, I'm utilizing reactive power. I'm pushing reactive power through the load or through the infrastructure to get to the load. Okay, so I had to put a larger conductor and a larger transformer in to supply that load. So you can't add a capacitor bank at the load and reduce the kVA or reduce the reactive power flow through the line and therefore reduce the size of the conductors. So increased system capacity is another concern. You can get away with a smaller transformer if you have a good power factor. Independent power producers often have to meet an interconnect requirement, and this is true around the world. You want to connect a renewable power plant to the grid. They want you to be able to run near unity power factor, but also even be able to supply reactive power into the network, because the network needs reactive power. You cannot have power flow without reactive power. So it's expected that generators or steam turbine generators, for instance, renewable power plants, that they all can produce a fair amount of reactive power. Oftentimes a power factor of 0.85 lead is required so that they can supply the necessary reactive power requirements of the system. Reactive power is often associated with voltage. Okay, if I can supply reactive power at a location, I can push up the voltage at that location, because VAR flow through inductance creates a voltage rise. And so from a utility standpoint, so we went through industrial customers, we went through power producers, the electric utility, the people supplying electric power. Most oftentimes, their interest is in reducing losses. If you think about the power, if we're pushing more current through the line because the poor power factor, it's I squared R. I squared times the resistance of the distribution line. If I can reduce I reduce losses. So from their standpoint, they can install a very simple pull mount capacitor bank out on a distribution line somewhere. They can reduce I at that location and back towards the source, and subsequently reduce losses, I squared R losses. They also have long distribution lines, oftentimes 20, 30, 40 miles long. You kind of see one strung here. There was a fair amount of inductance associated with that long distribution line, and then it's I times X. I times X is the voltage drop along that line. So if I can, that's I times R too, of course, I times R and I times X. But oftentimes X becomes the major component in a overhead distribution line at 13.8 kV or at 38 kV because of spacing, and therefore I have a significant amount of voltage drop along the line. And then system capacity, same thing. The utility does not want to install larger and larger transformers because of poor power factor. And it is the reason why many utilities will charge a penalty, as we noted up here. They charge a penalty because they want their industrial customers to behave in the correct way. And this is a way to push them into behaving in that way. It kind of makes sense if you think about it. A utility customer with a poor power factor will require a larger distribution line to their facility, a larger transformer outside their facility. If the utility, if they don't correct the power factor, the utility has to supply it. So how do they supply it? Well, they force the cost back onto the customer through a power factor penalty. That's the synopsis of how it all comes together. So power factor correction. talk about power factor correction. It's the process of adding reactive compensation or VARs, in this case, and a lot of times capacitor banks, to a system to improve the system power factor. So reactive compensation can come from various sources. These include capacitor banks, harmonic filter banks, and oftentimes capacitor banks are termed detuned capacitor banks, but it's still a capacitor bank. And harmonic filter banks also supply reactive power. So the number one reason why harmonic filters are installed on a system, number one is reactive compensation. Number two is the prevention of resonance. And then number three for harmonic filtering. So most industrial loads are producing some level of harmonics, but typically the harmonics are not an issue. Filters are often installed to prevent resonance or preclude resonance so that they can add reactive compensation to the system. So remember, filters supply VARs just like capacitor banks supply VARs. There is an inductor inside a filter, but that inductor is relatively small. A fifth tune filter, a good rule of thumb is take the fifth or the 5, square it, and you take X of C as a capacitor divided by 25. So it's 1/25th, the inductive portion of a filter. And that's a fifth harmonic filter. There's a question about what is the utility requirements in Australia. I do not know what goes on in Australia, and maybe some other people in the chat box can answer that question. The question is, any idea what is utility requirements for power factor in Australia? It would be nice if somebody could potentially answer that question. Okay, and it's another statement was we need to install cap banks and wind farms to provide Q reactive power. Correct. So primary reasons, remember, industrial and commercial customers, it's for potential savings to remove power factor penalties. Power factor penalties typically come in two forms. One is KVA billing, and if you're being billed on KVA, you can easily reduce your KVA by adding a capacitor bank of an appropriate size. So you can make the KVA equal to the KW if you do the amount of reactive compensation up to 1.0 power factor. It's always our recommendation that you go to a 1.0 power factor, and that will always give you the lowest amount of KVA. KVA billing tends to be a more costly to the industrial customer than power factor penalties. So power factor penalties, what you often see is they'll take the KW, utility bills have a KW demand, which is what was the maximum 15-minute KW in demand in the system, and they'll divide that by the power factor. They divide by the power factor. So if the power factor is 0.8, they divide by 0.8. So the customer indirectly pays for more KW because its power factor was not 1.0. So oftentimes you'll see KW demand divided by the power factor of the system, a 15-minute average or peak, maybe 15-minute average at the peak time of the day, will give you the new KW demand charge that the customer will see. And that can oftentimes be very, very expensive. So Jack answered the question. Is utility requirements for customers in Australia specifies a power factor of 0.8. They say this because they have power factor correction in the transmission system to bring it to unity. So that's an interesting statement. Power factor penalties in Australia are an industrial customer only has to correct a 0.8 power factor. So that's very different than what we have here in North America. Oftentimes we have to correct to 1.0 or 0.95 power factor. 0.8 is pretty low. That's a pretty low power factor. System capacity issues, and oftentimes we will sometimes get phone calls where an industrial customer keeps expanding, he's growing, and at some point the industrial customer is forced with saying, well, if we want to do another expansion, we need to put in a larger transformer because we maxed out our transformer. Well, some company like us might come along and say, well, your power factor is 0.8, and if you correct your power factor to 1.0, we could release 20% of the kVA of your transformer. And this is really what oftentimes is done. It's about, you know, cost options here. Do I buy a new transformer, or do I correct my power factor and stay with my current transformer? And that's an economic analysis. So power factor 0.8 lagging to go to unity would release the system's capacity of 20%. We could then push 20% more power through that transformer, may avoid the cost of a new transformer. So lots of good things in the chat box. I'm glad that everybody is working through the chat box here. The formula for kVA released is shown here to the left, and it's 1 minus the power factor initial divided by the corrected power factor times the kVA initial. So you can see here that if you improve your power factor, you can easily release some system kVA. The formulas are very simple to use. Let me go back here. Improved voltage regulation. This was another reason. This is the phasor diagram for voltage drop across a network, and you can see here you have IR cosine theta component, which is a voltage drop component, and you have a IX sine theta. And you can see here that the IX sine theta oftentimes represents a larger voltage drop in the network. So if we're trying to improve voltage regulation in the system, you can easily do that by improving the power factor. And so when we talk about voltage regulation, we're talking about improving the voltage from no load to max load. And oftentimes tap changers are put in place to help maintain secondary voltage levels within the plant. As the plant comes up in power, the voltage drops because of I squared or IX, and IX typically through a transformer, because X is the X over R in a power transformer is typically about 25, so say 20 to 25. So it's primarily the reactive component. So by reducing the power factor, or the IX sine theta component, as you see here, we can reduce our voltage drop significantly there. So improving power factor is by far the best way to go. Electric utilities, we will kill the voltage regulation again, but loss reduction. And so loss reduction is a big deal with utilities because of the long distribution lines. And the power losses along the distribution line for power flow, as you see up here, would be 3 times I squared R. 3 times I squared R. So a percent loss reduction formula here is 100 minus the power factor initial divided by the power factor corrected squared times 100. So you come up with your percent loss reduction here. And I think I do an example. So percent loss reduction. Here you can see if we go from a power factor of 0.75, to a power factor of 1.0, we can reduce our losses in the distribution line here by 43%. So it's pretty significant amount of loss reduction that you can get. Oftentimes I will get this call, and again, NEPSI does reactive compensation, power factor correction. We get the call from a customer who says, I want to justify a capacitor bank based on loss reduction within an industrial plant. I'm going to tell you that in 25 years of doing this, we have never justified the purchase of a capacitor bank because of loss reduction. What goes on in an industrial plant is different than what goes on in the utility distribution system. So just remember that typically you cannot justify reactive compensation with loss reduction within industrial plants. It's just not justifiable. And it's because the losses are relatively small inside an industrial plant for power flow, especially compared to power consumption. So it's usually very, very, very small. Never justified it, and we don't even entertain the the application anymore if a customer wants to justify on that. So we do have industrial utility customers and utilities in the United States. There's a good couple hundred electric utility providers in the USA, and many of those utilities do not have power factor penalties at all. And sometimes you get an engineer who wants to justify the purchase of a capacitor bank on loss reduction, and it just doesn't happen. Power factor correction illustrated on the power triangle. So we're back to the power triangle, and we start with this top triangle here, the largest triangle, the one outside the gray here, and this is our initial kVA and our initial value of Q here. When you add reactive compensation, you're drawing the arrow down. So you have a certain amount of VARs here on the y-axis, or the J component right here, and we're adding some value of capacitance in VARs or in kVAR or megavars here, and we're bringing that down. So we obviously can have QT and QC equal, and we would have a power factor of 1. So the formulas for calculating the change in power factor, in my opinion, is easiest done with a calculator. I kind of show the calculator here, and I always use this equation up on top, and it's really the tangent theta minus tangent theta prime times the power. So power is constant during reactive compensation. When we do reactive compensation, the P remains constant. What changes is the power factor, theta and theta prime. So you can always say arc cosine of the angle, okay, arc cosine of the power factor to come up with the angle. And so typically a customer might say, well, I got a power factor of 0.8. So I would say 0.8 F arc cosine on my calculator, and that gives me the tangent. And I enter that, and I could say, okay, 0.95 might be my corrected value, arc cosine, tangent again. Subtract those two values, I get a multiplier, and then I multiply it times P. So if you just put that one formula to memory, it's a very, very easy way to come up with reactive compensation, and very easy to do with a calculator. Another way, if you don't want to put the trigonometry to memory, is to use a table. And this is a very popular way of doing it. You have a power factor table, a multiplier table here, and basically you enter into the system here with your desired power factor. You have your current power factor, so I want to go from 0.75 up to a value of 0.93. So value 0.75 to value 0.93, and you come up with a multiplier of 0.487. Take the 0.487, multiply times the real power of the plant, and you'll come up with the size of the capacitor bank in VARs or in kVAR or in megavars, depending upon what unit of power you're using, to come up with the amount of reactive power that you need. Okay, so this is the way it's done, and I'll get to the one question in a second. This table is based on this formula here, so it's easy to develop this table from this formula here. That's how it's done. So I wanted to make a statement. So somebody's asked me, can you explain once more the power factor correction with harmonic filters? So what I'm saying is harmonic filters are applied for 3 reasons. Number 1 is power factor correction. Harmonic filters are installed for power factor correction. Number 2, you install filters for the prevention of resonance, okay, for prevention of resonance, or to preclude resonance. And there's the harmonic analysis presentation, which I'm going to do on September 1st. September 1st is a Wednesday, same time. We'll be discussing resonance and is this concept. So number 2 reads the prevention of resonance or to preclude resonance, and then number 3 is harmonic filtering. When you design a harmonic filter, typically you design to the 5th harmonic or the 4.7th harmonic or 4.0 harmonic. And what that means is we push all the resonances down below that tuning point on the system, okay? But to do that tuning, the inductor, okay, you basically take the tuning, you take the X of C, the capacitor reactance of the capacitor bank that you need, and divide by the tuning point squared, so 1/25th. So if you think about a harmonic filter, it consists of a capacitor and an inductor. Capacitor and an inductor. The inductor for a fifth tune filter is about 1/25th the reactive value of the capacitor. So therefore, a filter bank behaves like a capacitor bank, okay, for all frequencies below its tuning point. All frequencies below its tuning point, including the fundamental. I hope I answered that question. The power triangle is drawn in all four quadrants, okay, and this is a PQ load diagram. We're typically operating here in quadrant number 1, and this would be a typical industrial load. When you correct the power factor, you come down into, it sometimes can come down into this fourth quadrant here, where we have a value of negative Q and the system's leading. Okay, so just to make you aware. Power factor correction, application, solution steps. This is really, we won't get into it too much because we're running out of time, but I wanted to get into what the side effects of correcting power factor are before we finish up today. But typically, for power factor correction applications, the first thing is to determine the reactive power of the load. If it's an existing customer, look at their electric utility bill. It's the best place, especially if they're being penalized. Remember, the measurement protocol used by utility is to use 15-minute demand periods. It's not the same as going up there and taking a measurement at one point in time and thinking that you have it all figured out. So if you're doing a power factor study and you're trying to determine how much power factor correction I need, the best place to go is the utility bill. Look at the electric utility bill. You can always look at switchboard meters, the power quality meters at the incoming. Good location to get a general feel for, well, how big is the plant, how poor is the power factor. Take some measurements right there. And then, of course, you have load flow studies. If it's a brand new plant, you're going to do a load flow study using ETAP or Dixieland or whatever program is typical for your location. So you're doing a load flow study, and sometimes you're doing a load study. I take all my values, I put them on a spreadsheet. I got a p-value, a q-value, and I do a straight addition inside a spreadsheet, and I come up with my reactive compensation value. So from there, you're going to say, well, what is my tariff structure? What am I going to be charged for power factor? I have to look at the interconnect requirements if it's a renewable plant, and determine how many steps of capacitor banks I need. Step size is really dependent upon how much voltage rise I can get, and also do I meet the power factor penalty requirements of the company I'm doing it for, and then I calculate payback. And really, the decision to buy capacitors is based upon it's an economic decision. We got to determine a location. Remember, reactive compensation can be done at many locations. You oftentimes hear this concept: do it as close to the load as possible. The reality is nowadays we are not supplying reactive compensation at each and every load. It used to be back in the 90s when I started working in the power systems. It was oftentimes that a capacitor was placed at each and every motor within an industrial plant. That philosophy is no longer followed. Most oftentimes, larger capacitor banks are being applied at the load center rather than at each individual load. There are resonance concerns when installing capacitor banks on a network. We'll be talking about those on September 1st. You always should be thinking about harmonic resonance whenever you're installing capacitors on a network. If you have a resonance issue or a resonance concern, then you're moving towards a detuned capacitor bank. Detuned capacitor bank basically means a 4.0 or a 4.2 or a 3.8 tuned capacitor bank, or a filter, which is typically classified as a 4.8 or 5.0 tuned system. In my opinion, whether it's detuned or cap bank or a filter bank, they're all the same thing. It's a capacitor bank tuned to a frequency. So my sense, my way of thinking, is a tuned bank, is a filter bank, period. Typically, if you're a consultant, you're going to develop specifications. If you're involved with power factor studies and you're developing specifications, the NEPSI website, www.nepsi.com, we have a good 15 different specifications depending upon the type of plant. Are you an industrial plant? Are you a renewable plant? And so on. So are you a mine application? Because the flavor of a cap bank or filter bank changes depending upon the type of facility you are in. So we have different specifications for that. But you also have open air versus metal closed reactive compensation solutions. So you have to think, do I want a metal closed solution, kind of as you see behind me here, or do I want an open air solution where everything is exposed to the environment? Protection and control. Cap bank is more than just a capacitor. You got to switch it on and off. You got to have a disconnecting means. If it's metal closed, you got to have cooling requirements, and then there's switching operations. So there's more to a capacitor bank than just a capacitor. You got the balance of the system that you need to be concerned about. Site requirements, how much footprint do you need, so on. And then there's bid evaluation. So when you do reactive compensation, the question becomes, where do you do it? I've kind of mentioned this already. You can do it at the motor, okay, at each and every motor. This is really a practice that's really not followed nowadays. You do see it once in a while. This creates a very complex system from a resonance standpoint. If you were to look at the impedance scan of this system, you would see a very jagged impedance scan, very difficult to predict the harmonic response of the system for that. You also have the possibility of doing reactive compensation at the 480 volt level, at a medium voltage load center, again at large medium voltage motors, or as a open air or metal closed system right here on the main bus bars, and you can step up through the system. We generally recommend that you do reactive compensation at one of these locations. And they'll do all the locations, because the more capacitor banks you put in the system, the more complex the impedance profile comes from a harmonic analysis standpoint. And whenever installing capacitor banks, remember, harmonic resonance is a concern. Primary concerns when adding capacitors to a network: overcompensation. We see it all the time. Customer will call and say, I want to buy a capacitor bank, but I cannot go leading. The reality is that going leading is not a big issue. Power factor meters, as I show here, they go from a minus 0.5 to a plus 0.5. So we got capacitive, and technically speaking, it's not minus 0.5, it's 0.5 capacitive, 0.5 inductive. Whenever you talk about power factor, you have to say capacitive or inductive behind it to make sure you define what it is. It's not really negative. So if you overcompensate the system, typically you will get an overvoltage, or you can have an overvoltage. But the reality is it takes a lot of capacitors to create an overvoltage condition, and typically going leading a little bit is not going to result in a high voltage concern. The calculation is very simple. I'll show you the formula in just a moment. Harmonic resonance, I noted that already. Whenever installing capacitors, always be concerned about resonance. Voltage rise and drop during switching. The general rule of thumb is if I switch a capacitor bank on, the standards want to keep me at 3% or less. So I say I need 15 megavars for a system. The question is, can I switch all 15 megavars on at once, or do I need to break the 15 megavars up into, say, 3 steps of 5 megavars? The primary criteria for determining how many steps to break it in, one of those is 3% voltage rise. I want to make sure I don't have more than 3% voltage rise. You might want to even consider 2% voltage rise. So we split the bank up into smaller pieces by coming up with, well, what creates a 2% voltage rise, or what creates a 3% voltage rise. Typical situation that you got. Switching transients is, in my opinion, is very seldom an issue at the 34.5, in your case 33 kV level and down. We oftentimes have customers concerned about it, but I can tell you in all the years that we've been in business, about 26 years now, over 2,500 systems sold, I only had one voltage transients issue in all those years. So switching transients is often a concern, but typically we never see it. There is technology out there, point-on wave switching, and oftentimes called zero voltage closing, or point-on wave switching. And then you have pre-insertion resistor technology. All those look to mitigate switching transients. In the renewables area, most oftentimes we are dealing with some type of transient mitigation switching device. And the ones that we typically use either use pre-insertion resistors or point-on wave switching, but only at 34.5 kV or 33 kV in other parts of the world where we see that technology being used. There are outrush current concerns in the substation for nearby faults. When there's an outrush from a capacitor bank to a nearby fault within the system, oftentimes the breakers in the substation might need to be uprated, and I think I'll show that in motor excitation. So let's go through system resonance concern. I put a capacitor bank here in the lower left of the bus bars, and I will create a resonance in the system. Again, on September 1st, we'll talk about this. So installing capacitors here to create a resonance. You can calculate the resonant harmonic very easily here by this formula, kVAR divided by kVA short circuit square root. And really, the kVA short circuit is related to the impedance of the network here. Okay, so just remember, in this case, if I have resonance near a value of harmonic current that exists in the system, so VFD drives produce 5th harmonic, 7th harmonic, 11th harmonic, 13th, 17th, 19th, and so on. This is also true for rectifiers, 5th, 7th, 11th, 13th, 17th, 19th harmonic. And if you have high post devices, you may have a 12 post device. Theoretically, it will not produce a 5th and 7th harmonic, but the reality it does. It produces low levels of 5th and 7th. Resonance is a peak in the impedance waveform. It can be very high peak. It can magnify very low levels of harmonic current and cause problems. So whenever you calculate resonance near a 5th or a 7th or an 11th or a 13th, be aware. Be aware of the situation. You may have a problem if you go ahead with that system and not install filters. So voltage rise is the other concern we talked about. The formulas for calculating voltage rise and voltage drop are very easy. You see here I'm saying 1.5 to 3% per switching step. So if I need to come up with my switching step, I'm using this formula here. What size bank can I put in based upon the short circuit impedance of the network, which really determines the impedance of the source. And really we're talking about I times X. I, the capacitor bank, times X of the source impedance gives you voltage, right? And that's the voltage rise I get here. So if I switch capacitor bank here, I get a voltage rise at this point every time I switch a step in. Okay, and that's calculated with this formula here. So very, very simple calculation. Switching transients, this is a classic switching transient. Remember from college years, when you energize a capacitor, the voltage across the capacitor cannot change instantaneously, right? That's what you remember from college years, which means that at the moment you switch, the voltage will drop to 0, okay? And because the voltage across that capacitor can't change instantaneously, and what you get is you get an overshoot afterwards, and that's what you see here. If you follow this red waveform, we're switching a negative peak here, and incidentally, it almost always occurs at peak. Vacuum contacts are closing, and as they close, you get a pre-strike around peak voltage before the contacts actually close. It brings the system voltage to 0, as you see here, and then you get an overshoot of about 1 per unit. So it's almost 1 per unit overshoot, so we get almost a 2 per unit voltage. Because of the decay in the system and the moving of the waveform, the value typically is about 1.7 per unit. But medium voltage cap banks, you typically don't have load at that medium voltage level, and therefore it's typically not a problem. But when you have very large banks, a zero voltage closing vacuum switch, a VD4 CS, for instance, from ABB, a cap switcher from Southern States, or the ABB DS1 switch, which is a diode pre-insertion resistor technology, can all be used to basically mitigate this voltage transient if it becomes a concern. I'm going to answer the last question from Victor in a moment. We're just about ready to be done here. So switching transients, you have to do inrush calculations. This is very easy. We have some stuff on our website on switching transients, but basically the concern here is that in a multi-stage capacitor bank, there's always a concern for the high rate of rise of current in the frequency of the inrush current when we're closing this last stage. So in this case here, we have two stages that are currently in a closed state. They're charged, they're in operation, and we're calling for this third stage to close. It closes around peak voltage, as I noted before. So at the point in time where it does close, you get a current flow, a high magnitude current and a high magnitude frequency, basically a DI/dt current flow through the contacts here as they're starting to kiss, and it can damage the contacts of the vacuum switch. Because there's very little resistance, very little inductance between stages in a multi-stage capacitor bank, they're right adjacent to each other, you get a very high current. So typically an inductance is added to the system, and that's what we show here. We add a little bit of inductance. 40 to 80 microhenries is all that is required. And that's it. There is a question from Victor. What are the critical maintenance tests inspections to be conducted on capacitor banks and harmonic filter banks? That's a big question. In my opinion, capacitor banks are very low maintenance devices, but at least on an annual basis, you need to be checking the capacitance and making sure the capacitors are healthy. You need to be checking the insulators to make sure there's no tracking. You need to be making sure the connection points are all torqued, because loose connections can result in failure of the capacitor bank. They are the three, I would say, the biggest ones. You want to check your switching device. How many times has it operated? Is there an over operation of that switching device? Are you switching too many times? Because there is a limit to the number of operations, typically 10,000 operations. So you want to make sure it's not switching too often. For harmonic filters, you want to check the reactors, make sure there's no discoloration in the reactors. You want to check to make sure the fans are operating, because fans are required to keep it cool. You want to make sure the filters are not clogged. These are real quick items. Okay. So let's go on to the next one. This is the inrush current calculations. Again, I would recommend you go to our www.nepsi.com, and there's a whole spreadsheet tool available to you there. Also, I'd like to mention, if you go to NEPSI's YouTube channel, or go to nepsi.com and go under videos, NEPSI has about 50 tech talks on capacitor bank design, harmonic filter design, inrush calculations, where we dive into great detail into these formulas, how we use them, how we got factory visits where we go out to the factory, we do in-post testing. Some really good tech talks that we've done. I encourage you to go do that. This is an example of that inrush current calculator tool on our website. They're all, you can download them and put them into Excel yourself and use them. They're great tools. Transient outrush is another concern that we often see, and this is let me walk you through what this is. In transient outrush, the concern is related to a fault that might occur here at X. You see the X under BH4. What happens is, if I have a permanent fault, say I have a cable leaving the substation, and a shovel digs into it and creates a fault in that cable, a permanent fault. The first thing that happens with BH4 is it opens, but then which then allows that capacitor bank to charge again and to go into operation. But at some short period of time later, because of the desire to clear a fault and then to re-energize for reliability issues, the BH4 breaker recloses automatically, or maybe a guy goes out to the substation and closes it manually. But the fault is permanent, and all of the charge within this capacitor bank dumps into that point there. There's very little inductance between that point right outside the substation, basically on the low side terminals of the BH4 breaker, and we exceed the momentary rating of the breaker. So in these cases, we need to add an outrush reactor here. And the calculation for that is also on our website, and you can check it out there. There's a spreadsheet tool for it. But the formulas, again, are fairly easy to calculate that outrush current. Essentially, sometimes it pushes you into what's called a C2 rated breaker, a breaker that's been designed for capacitor switching. But there's a cost associated with that because they're all special breakers. So, spreadsheet tool again. So, typical outrush reactors here, basically a coil, sometimes about 100 to 200 millihenries is what we would typically see. Typical wind farm application here, I show you the outrush reactors on top. Okay, so we had bushings coming out, going through outrush reactors here. So very, very typical application. So motor excitation, I won't get into that too much because it really doesn't happen nowadays. But essentially what we're trying to prevent is too large of a capacitor bank being applied at the terminals of a motor. You cannot overcompensate a motor at the motor terminals. It will put the motor into a self-excitation condition and can overvoltage and actually fail the installation in the motor itself. So general rule of thumb is never size the capacitor to be more than, say, 90% of the reactive compensation requirements of the motor at no load. So measure the current at no load in a motor. The capacitor bank should not draw more than 90% of that in current. So again, a bunch of resources here for you guys to check out. And there's a NEPSI Tech Talks. I'm telling you, they're great Tech Talks to also evaluate. So remember, I appreciate, number one, that you come on today to listen. September 1st, I'll be back with you to talk about harmonic analysis. If there's another subject, reach out to the folks at EESA and let them know. If there's another subject related to reactive compensation, my expertise is reactive compensation, harmonic filtering, anything to do with that, medium voltage systems. I'm really an expert on capacitor bank design, harmonic filter design, and harmonic analysis. So I tend to lean in that direction. We will be doing September 1st harmonic analysis, and then December 1st filter design and how to actually design harmonic filters. It'd be really a hands-on approach and how we approach it. Remember what NEPSI does. We build cap banks, filter banks. If you got a project, just reach out to me, paul.stechik@nepsi.com. You can also reach out to John Wright Smith. He was on the first slide of this presentation. They build StatCom systems, which is a power electronic version of a capacitor bank. It's it supplies instantaneous reactive power to the network in less than one cycle of time. So it can really mitigate voltage sags associated with motor starting and provide dynamic voltage support to the system during fault conditions. We oftentimes see it being applied in chip manufacturing plants to support voltage during power system faults outside of the network to support voltage, because capacitor banks will prop up the voltage during a fault because it supplies reactive power. And a StatCom can do the same thing. That completes the presentation today. This Tech Talk is recorded. It will be at this address forever if you need to refer to it. And don't forget PDA certificates. If you want me to send you a certificate, send me an email, paul.stechik@nepsi.com. and I will get you your certificate for today's presentation. Just send me a code and say 123, and it will let me know that you were here, and you can then maybe apply it towards your engineering continuing education requirements. And thank you.